Great. So thank you again. Okay, so I didn't get through all the physics yesterday, so the updated graph is like this. So there will be still more physics today, and then the amount of physics should decrease. So let me just remind you briefly of where we were last time. So we had this dictionary where the main players were like this. So there was a Riemann surface, one-dimensional complex manifold C, together with an ADE Lie algebra, which I called script G. And somehow the main story that I'm trying to tell you something about is that given that data, you produce some supersymmetric quantum field theory, so-called field theory of class S. Okay, and we just record that it depends on that data. And I told you some aspects of the dictionary. So the moduli of the Riemann surface, so the deformations of the Riemann surface correspond to deformations of the field theory, which we call the couplings. We had the surface might or might not have marked points. It doesn't have to have marked points, but often it does. And if it does, they correspond to some symmetries of the field theory. So for example, in the A1 theories that I showed you, each marked point corresponded to some SU2 symmetry that the field theory would have. I told you that gluing, if you have two surfaces and you glue them together with a tube, that corresponded to gauging some of the global symmetry, some subgroup of the global symmetry. So gauging, if you never thought about this, gauging is some kind of, it's like the quantum field theory version of a quotient, but it's a relatively sophisticated thing in the sense that, in particular, if you start with a free theory, a theory with no interactions, gauging it introduces Yang-Mills fields, gauge fields. And so typically it'll make the theory a more interesting interacting theory. Okay, and then the last thing was I said that the mapping class group, so kind of well, not exactly symmetries of the surface, right? Because they're not automorphisms of the surface, but they map a surface to generally one with a different complex structure. Those corresponded here to the duality symmetries. Which map a theory with one coupling to a theory with a different coupling. Okay, and today, hopefully by the end of today, we'll add at least one or two more entries to this table. So for example, one thing I hope to explain is that the Coulomb branch, sorry, wrong side. So for n equals 2 theory, as Professor Arakawa was explaining in his lecture, yeah, so let me emphasize, by the way, so here I'm talking about n equals 2 theories in 4 dimensions, really the same category of theories that Professor Arakawa was talking about. I guess you didn't talk much, actually, okay. So you talked about Coulomb branch, but not about this Coulomb branch. So the Coulomb branch of the 4-dimensional theory. So I'll call that MC, maybe for emphasis, I'll write MC4D. So this is a slightly different Coulomb branch. So this one is going to correspond to the base of Hitchin's integrable system. So I'll just write B of, and of course it depends on the same data. Everything here depends on a Riemann surface and a Lie algebra. So Hitchin integrable system also depends on exactly that data. Okay, so that'll be the Coulomb branch. Okay, and then you wonder, what about the actual Hitchin integrable system? Okay, that'll also show up, but not exactly as this Coulomb branch. So we'll see where that shows up. Okay, and so let me just say a little bit more about the kind of dictionary here. So we talked about our kind of basic example was a sphere with 4 punctures. a sphere with 4 punctures, um, and we're taking this basic Lie algebra to be always A1. And then we said the way we think of it as a quantum field theory is, well, the way we describe this quantum field theory concretely is to think of decomposing this sphere into two, people would call it pair of pants, or physicists say trinions, these 3 punctured spheres. And the 3 punctured spheres are somehow the most elementary thing. We can't decompose them further. They don't have any moduli. Oh, sorry. This is bad habit. So yeah, when I say puncture, I mean the same thing as mark point. If I'm careful, I'll say mark point, but often physicists often use the word puncture for this. It's hard to avoid that. Yeah, that's right. So in order to concretely say what this quantum field theory is, we think of decomposing the sphere into these elementary trinions. And then we got a description where here I have the free theory, which only has, so it has no gauge group. It just has the matter. And the matter was c to the 8. Here was another copy of the free theory with E equals c to the 8. Sometimes we call this theory the theory T2 because, so I guess it's T for trinion or 3 punctured sphere, and the 2 is for SU2. So we have 2 copies of the free theory. Then we take the direct sum of them. And what the gluing means is we take a quotient, and by quotient I mean gauging the symmetry. We gauge some diagonal SU2. So this direct sum of free theories is acted on by 2 copies of SU2 cubed. We have the SU2 cubed Flavor symmetry here, the SU2 cubed Flavor symmetry here. We take the diagonal of these 2 and we gauge it. And that's the definition of the field theory that you get here. Physicists sometimes call this theory the SU2 theory with 4 flavors. The 4 somehow comes from the fact that we have c to the 16 here. And you think of that as 8 quaternions, but they're acted on by SU2, so it's 4 fundamental representations of SU2. Okay, anyway, that's just a jargon for it. But you'll see this jargon a lot. So the SU2 theory with 4 flavors. Okay, fine. And then I said, okay, well, there's various, you learn various things about this theory from realizing it in this way. For example, there's 3 different ways of decomposing the sphere, and so you get 3 theories that are not obviously the same, but they're supposed to be the same. Let me show you a couple more examples just to get a feeling for how this business goes. Yeah. Yes. Yeah. Yeah, I'll mention the elliptic curve with 1 puncture in a sec. But before that, let's talk about a sphere with, let's say, 5 punctures. So 5 punctures. 1, 2, 3, 4, 5. So this one, so again, we get some quantum field theory. Now this quantum field theory has 2 parameters rather than 1, because the moduli space of spheres with 5 punctures, you can fix any 2 of them by SL2C. So this will be a quantum field theory which should have 2 couplings instead of 1. How do we see the 2 couplings? Well, we imagine degenerating this. So now we could degenerate it to like a chain of 3 spheres. So we have a 2 punctured sphere that's glued to a 1 punctured sphere that's glued to a 2 punctured sphere. So the picture is like this. And so now this is a theory where we started with kind of, c to the 8 plus c to the 8 plus c to the 8. So we have kind of c to the 24 worth of matter. And now we're gauging we're gauging now two SU2s. So yeah, so now I have two couplings. I'll call them Q1 and Q2. And so we'll get a free theory with this amount of matter. Again, you gauge a group, and now you gauge the group SU2 times SU2. So we're producing a gauge theory where now the gauge group is not just SU2, but it's some product of SU2s. And in general, that's the kind of thing that'll happen. So if you take a six-punctured sphere, so this one now I can decompose in two ways that even kind of look different. So one thing I could do is I could take a chain. Okay, now forget the colors. I can make a kind of linear chain. Another thing I can do is I can make a thing like this. Okay, so put 2 mark points here, 1, 1, 2. So there's the 6 mark points. And on this one, I have 2 here, 2 here, and 2 here. So if you work out the description of the quantum field theory, you'll see here that you got 2 different quantum field theories. In both cases, you're taking, matter, I guess C to the 32. But here your quotient, here you have a SU2 acting in one way, SU2 cubed acting in one fashion. Here you have SU2 cubed acting in a slightly different fashion if you work out, what are all the diagonal subgroups and so on. And so here you're getting 2 absolutely different quantum field theories. The description of them looks really different. And the prediction of this class S story is that those 2 quantum field theories are actually secretly the same. There's a duality symmetry that relates this one to that one. And then, of course, you see that you can make many more things of that kind. So in that sense, this class S business is supposed to give a vast new class of kind of quantum field theory dualities that you can play with. So this observation, I should say, so this stuff is described in Davide Gaiotto's paper, which is called N equals 2 dualities. He described pretty clearly this story. It's a beautiful observation. Okay. So yeah, so another example. By the way, not to be confused, some people have probably heard of or thought about gauge theories that are determined by quivers. So remark, one popular way of getting a group and a representation, so a group and a representation would be to make a quiver, right? Where you have nodes that correspond to groups. So you write like, UN, UM, UK, and then you have the links correspond to the fundamental representation. So here you put like Cn tensor C to the M, acted on by the 2 factors. Here you put C to the M tensor C to the K, acted on by the 2 factors. So you build a group, which is just the product of these groups, and a representation, which is the direct sum of these representations. And those kind of gauge theories, called quiver gauge theories, are a very well studied and important subject. What I want to emphasize is that is not what we're getting here. Produces something different. So here, right, the representations are associated to these 3 punctured spheres, and each one of them is acted on by 3 SU2s, not by 2. So here you have the bifundamental. In this class S business, you're producing always trifundamental. So you could call it kind of generalized quiver. And if you look in Davide's paper, he drew pictures like this, where you have. So you could get a thing like this. Yeah, just draw like So yeah, I guess the way you usually complete the picture is you would make some of these flavor symmetries. So the ones that you don't gauge, you draw a box. So maybe we would draw it like this. Yeah, so here I have two trifundamentals and right, just one gauge symmetry. In fact, this is the picture of that one in this generalized quiver notation. So okay, so okay, so I just want to say these are not the quiver theories, but it's some kind of well-characterized class of groups and representations that you get. Okay, so then one more example. One more example. Let's think about a torus with one puncture. So how can I think of getting a torus with one puncture in this business? Well, I could think of getting it by starting with a three-punctured sphere. And now I glue in a handle which glues it to itself. So that'll produce something with the topology of a torus, but with one puncture left over. And so what is that? That's a gauge theory. So it's a gauge theory with, so you see just one cylinder here. So the gauge group will be SU2 to the first power, with coupling Q, the modulus of that cylinder. And the matter representation, so if I take C2 tensor C2 tensor C2, and then I look at it as a representation of, yeah, so what are we doing? So we're taking C2 tensor C2 tensor C2 as a representation of SU2. So here's SU2 times SU2. Inside of here, I take the diagonal. Then what representation am I getting? I'm getting the I'm getting the tensor product of two fundamentals. So I get the adjoint plus the trivial representation. And so E will be as a representation of the gauge group, it'll be adjoint plus trivial tensor with C2. And this is a field theory which is not exactly okay, so as I described it, it's an n equals 2 theory. Actually, this particular n equals 2 theory is very closely related to the n equals 4, the most special one. So if I didn't have this trivial piece, if I just take n equals 2 and add one more adjoint, then what I'm getting is n equals 4 super Yang mills. And that's related to the fact that here we have the torus, the mapping class group of the torus would be SL2Z. So the SL2Z symmetry that I told you of the n equals 4 super Yang mills shows up in this story as the SL2Z symmetry of this particular torus. So in some sense, this story contains the story that I told you before of n equals 4 super Yang mills. So this is kind of an accident for this particular surface. Usually you don't get n equals 4. Usually you just get n equals 2. In this particular example, you get almost the n equals 4 theory. I mean, the moduli spaces are the same, but I don't want to say that yeah, oh, one is a double cover. Yeah. Yes, that's right. That's right. We're not saying it's the same theory. Absolutely not. Right. One of them is the theory with 4 fundamental hypermultiplets. The other one is this theory with the adjoint plus trivial representation. So yeah. Okay. Okay, so maybe that's enough of examples of this business. So I should talk at least a little bit about the cases of other Lie algebras. So I talked so far just about the Lie algebra A1. Let's talk a little about what you get for other Lie algebras. So let's talk about general A type. Let's see. Yeah, go here. So let's take A n minus 1. So here there's a similar story, but there's a little more data. So there's some additional thing that we're allowed to do, namely, sorry, each puncture, each mark point. At each mark point, we'll decorate it by a partition of n. Or people usually codify this as a Young diagram with n boxes. So there are a few that come up a lot. So there's the so-called full puncture or full mark point that corresponds to this partition. So it corresponds to the Young diagram, which is just a column, right? F for that. There's another one which is called the simple puncture, which is n minus 1 comma 1. So that's this Young diagram. You might think that you should also consider this one, which is just a row. But that one's actually completely trivial in this story. So putting the row is the same as putting nothing. So that means for A1, the only non-trivial choice is to put this Young diagram. But as soon as we get to A2 and beyond, we have some choices. And so the quantum field theory that we get will depend on that. Will depend on which Young diagrams we put at the punctures. And I told you that the punctures, the mark points, have to do with the flavor symmetry. So I should say, what's the flavor symmetry associated with each one of these kind of punctures? There's a general rule, but let me just tell it to you for the full and the simple one. So for the full one, it's SUN global symmetry. And for the simple one, it's U1 global symmetry, as long as n is bigger than 2. Or n equals 2, it's accidentally SU2, because then these two are the same. Okay, so there's some rules about this thing. And now trivial has nothing, has no symmetry associated with it. It's literally the same as putting nothing there. Okay, so now again, you can go and try to build interesting quantum field theories out of this structure. And so there are sort of two basic examples. You can use any Young diagram. Yeah. These two are just the ones that somehow come up frequently. If you start looking at papers about this stuff, people are constantly talking about full punctures and simple punctures. But that's right, you can use any Young diagram. And so for example, again, you try to kind of make things out of basic building blocks. So here, the most basic building block is to do the following. It's to do, and now the rules get a little bit Byzantine. So it turns out the good thing to do is to do 2 full punctures and 1 simple puncture. And then what you'll get, this is kind of the analog of what we had for for T2. So we'll get, again, a free theory. So this is one we can completely understand. It's corresponding to a vector space, which is now C2 tensor C to the n, tensor C to the n, acted on by these flavor symmetries. So U1 here, SUN here, and SUN here. And then we can again do things like gluing them together. So we can take two of these things. So I can take simple, full, full, and glue it to simple, full, full, glue the two full punctures together. And so that'll correspond to a field theory, which is like, okay, so here I've got C to the 2n squared. Here I've got C to the 2n squared. That's a free theory. Now I gauge. Now I'm gauging SUN. So now I'm getting an SUN gauge theory. And similarly, by gluing together more of these things, we could get, again, Lagrangian field theories where I take some free theories and gauge some product of SUNs. That's one thing you can do. That's not the most interesting thing you can do, but that's one thing you can do. So here again, we get kind of generalized quivers. Of SUNs. You can glue, yeah, that's right. You can glue, in fact, I think I don't want to try to get into all the rules of this business. Let's just say you can glue full with full. So I'm not describing the most general thing, but I'm describing one particular kind of construction you can do. Then the more interesting thing is to consider the most fundamental one somehow is to consider the theory with three full punctures. If you understand the theory with full punctures, there's a procedure called Higgsing, which can produce the theories with other Young diagrams. So in some sense, the most basic thing is to understand the one with three full punctures. Then we can glue it together to make a bunch of full punctures, and then we can do this Higgsing to get all the other examples. This one is called, so we just call it theory Tn. And the interesting thing about it is that in the case n equals 2, I told you what it was. It was this free theory, because then it's the same as the full, full, simple. But for n greater than 2, this theory, as far as anyone knows, is not a Lagrangian field theory, meaning you can't get it by writing down an action. And so in some sense, this description of it, the description of it as the theory associated to the three-punctured sphere, is in some sense, it's the best description we have of the theory. So we can learn a lot of things about it indirectly, and I'll tell you some indirect things about it as we go on, but it does not have like a direct, concrete Lagrangian description. And in some sense, the way you're supposed to think is that most of the theories of class S are actually like this. They don't come from writing down some simple kind of matter and then gauging it. I'll just say one other thing. So for n equals 3, for n equals 3, this is a theory which actually had been discovered before. It was called the exceptional Minahan-Nemeshansky field theory, which has, it's a kind of funny thing. It's exceptional in the sense that it has E6 global symmetry. What do you see from this description of it? From this description of it, you see, realizing it in class S, what you see is kind of SU3 times SU3 times SU3. Well, if you draw the extended Dinkin diagram of E6, right? You can see a kind of SU3 times SU3 times SU3. In fact, this theory actually enhances, so it actually has E6 symmetry. Okay, fine. So this is just to say that in this construction, you get a bunch of Lagrangian field theories and you learn new things about Lagrangian field theories. But you also produce, in some sense, most of what you produce is these new quantum field theories, which you didn't have real direct access to before. This is the Dinkin. So if you want to describe the subgroups of the ordinary E6, you can describe them using, using the affine Dinkin diagram. Right? So that's right. This E6, I just mean the ordinary E6. I'm just saying that the ordinary E6 has a subgroup, which is SU3 times SU3 times SU3. Okay. Great. Okay. So I think that's all I want to say about the kind of the sort of generalities of the class S construction. Let me say a little bit about where this construction is supposed to come from. So I told you, some long story about there exists a quantum field theory for every Riemann surface and G of ADE type, but I didn't tell you where they're supposed to come from. So where are they supposed to come from? So okay, so the basic sort of miracle that physicists believe in is the following. It's that when you have a Lie algebra of ADE type, there exists a six-dimensional quantum field theory so it doesn't have a great name, but sometimes people call it theory X. So theory X, which depends now only on the data of a Lie algebra and nothing else, which is not Lagrangian, so we don't know how to describe it in kind of elementary terms. So all of its constructions somehow use, at least so far, all of its constructions use string theory in some way. So if I just say a six-dimensional QFT, there's a bunch of them, but this should have so-called n equals 2, 0 supersymmetry. And even more than that, it should be conformally invariant. So in particular, scale invariant. We use this language of conformal invariant sometimes, so I should say what it means. So 2, 0, it's because it's something about spin representations in 6 dimensions. So in 6 dimensions, we have the 2 inequivalent spin representations. I'm saying you take 2 of this one and none of the other one. And again, this is the maximum possible amount. There's a beautiful classification of the possible superconformal symmetry algebras due to Nahm. And in Nahm's classification, there's this exceptional one. And for a long time, no one knew whether it was realized by any quantum field theory. And then, I guess around like maybe 94. Okay, in the 90s, people realized that there is such a quantum field theory that comes from string theory. So it's and right. So n equals 2 in 6 dimensions. So you have to remember that the dimension of the spin representation changes as you go up. So this is sort of 16 odd generators, 16, which is the same number as n equals 4 in 4 dimensions. So 16 supercharges is always the maximum. And so here we're getting 16 supercharges in 6 dimensions. And you can't go higher. So in 7 dimensions, you would need to have 32. So 6 dimensions is the, this is it. This is it as far as anyone knows. It's conformally invariant. Conformal invariance, let's talk particularly about inside of that is scale invariance. Scale invariance means that this theory, if you look at it at long distances, you'll see exactly the same structure as you'll see at short distances. So any picture that you make out of this theory will be kind of invariant under rescaling. Those are kind of the most interesting quantum field theories. Some of the most elementary ones are the conformally invariant ones. If you have one that's not conformally invariant, you typically try to look at it either at very short distance or very long distance and try to find one that is conformally invariant. Here, this one is already conformally invariant. And now the idea is the following. The idea is that we'll take this 6-dimensional quantum field theory and we'll use it to make lower dimensional field theories. So how do we do it? Well, so what we're supposed to do is we put this theory x of g on a space-time of the form R4 times some 2 manifold. So it's a 6-dimensional field theory, so you ought to be able to formulate it on not only on R to the 6, but hopefully on any 6 manifold. And here you try to put it on R4 cross a compact surface. And then we look at it in the limit. Okay. I overlook some fine structure here. So for the experts, we have to be a little clever how we formulate it on this surface. So we use something called a partial twist. Anyway, with the correct kind of incantations, you can formulate it on R4 cross a surface and get a theory which is still supersymmetric. Then you take the limit where, so this is really a Riemannian object, and now where the area of the surface becomes extremely small. And then what survives is just a field theory in R to the 4. You don't see any more of these internal dimensions directly. So sometimes people call this compactification. It's not the same as what physicists mean by it's not the same as what mathematicians mean by compactification. It just means we took R6 and we made some of the dimensions compact. Now we take the limit as the area of this curve approaches 0. And in that limit, we produce a field theory, an n equals 2 theory in R4. And that theory is supposed to be this theory of class S. So that means all of its properties, in principle, we could determine from the properties of this kind of mystical 6-dimensional field theory. But that's the idea. That's why these things are supposed to exist. Okay. That's maybe not that useful because I didn't tell you, apart from telling you that there's some 6-dimensional QFT, I didn't tell you anything about its properties. What people use in practice, well, it's just an obstacle to, okay, well, 2 things. One thing is it's an obstacle to studying it by kind of the usual methods of, perturbative quantum field theory, which is one of the most powerful ways we usually study them. Here, yeah, I would say that's the main thing. It's just an obstacle. That's right. There's no perturbation theory. I mean, in fact, there's not even a coupling which we could have done perturbation theory in, right? I said it's just an isolated theory with no couplings at all. So that's right. So directly in 6 dimensions, we cannot study this thing by perturbation theory. So let me say a few words about how people think about this quantum field theory, because some of the mathematics of the story is somehow connected to this. So I said it comes from string theory. So So let me say kind of the string theory philosophy. So the stringy perspective on this quantum field theory, at least for A-type. So for A-type, well, actually, let's directly talk. Let's do it all in one step. So let me give you directly the stringy perspective on this compactified theory. So the idea is the following: is we study M theory. So in M theory, the spacetime is supposed to be 11-dimensional. And the 11-dimensional spacetime that we study is, it'll be R7 times the cotangent bundle to our surface, whatever it is. And so we're supposed to think that the cotangent bundle to the surface, so think of the surface as really a complex surface, equipped with some metric, and then the cotangent bundle is naturally hyperkähler. Okay, to be honest, not hyperkähler. Hyperkähler in some neighborhood of the zero section. So let's just imagine that we look only close to the zero section. So then we can think this is actually a nice hyperkähler space. That's the kind of background where you could, so in particular, it's Ricci flat. That's the kind of background where you expect to be able to formulate M theory. And now, so in M theory, the basic objects are membranes of different dimensions. And in particular, there's an object called the M5 brane. That's a 6-dimensional object. We put n of them. So I have to find a 6-dimensional submanifold inside of here. And the submanifold I'll take R4 cross C. So I pick some R4, so I could think that it's like, x1 equals x2 equals x3 equals 0 here. I have 7 coordinates, but I set 3 of them equal to 0. So then I get R4 here. And here I'll just take the 0 section inside of this cotangent bundle. And then we look at the low energy limit. So we look at the dynamics of the theory close to where we put these M5 branes. And then in the limit of low energy, we're supposed to see, first of all, we're supposed to see the 6-dimensional theory just living on R4 cross C. Then when I take C to be small, I'm supposed to see this theory of class S living on R4. Why am I telling you this? Because some of the mathematics later will involve curves sitting inside the cotangent bundle. And this is a useful picture of why we're talking about curves sitting in the cotangent bundle. The reason the cotangent bundle is there is somehow because of this. Okay. Maybe one remark about this picture, because 100%. Okay. So certainly, I mean, to be strict, right? Even quantum field theory is hypothetical in some sense, right? No one has completely defined even what is an n equals 2 supersymmetric. Yeah. So I mean, what can I say? So the hypothesis of M theory is something that sort of, it's widely accepted among physicists who grew up in my generation that this thing exists. Here, I think I should use it just as some motivation. I'm trying to explain why we're later going to be talking about curves in the cotangent bundle. For us, this is the reason why. But while we're here, let's talk a little bit about some kind of geometric symmetries in this story. So what do we see from this picture? What do we see from this picture? We see two kind of geometric symmetries. Okay, so of course we see again, ISO4 acting on the R4 part. But then we also see on the cotangent bundle of the surface, there's, okay, this hyperkähler metric is U1 invariant under the rotations of the fibers of the cotangent bundle. So this setup is invariant under rotations of the fibers. So there's a U1 in the story. And then also there's SO3 acting on, let's see, the orthocomplement of R4. So we have R7, we divide into R4 plus R3. On the R4, that's our spacetime, the spacetime of the class S theory. That has the usual ISO4. But I want to point out we also have kind of SO3 acting on the transverse R3. Or think of that as Z2 quotient of SU2. So the point is, in this geometric setup, you kind of see a U1 and an SU2. And those symmetries will show up in the field theory. Okay. Anyway, that's one kind of stringy perspective on where this class S theory comes from. I'll mention one other very quickly. Another stringy perspective, which is to make a Calabi-Yau threefold X fibered over the surface. So now I completely forget about M theory. So this is just another way of getting the field theory, which is different from the first one. I make a Calabi-Yau threefold whose fibers are ALE singularities. So let's say, in the case of AN-1, the fibers will be the, so again, hyperkähler singularity C2 mod Zn. You can make a Calabi-Yau threefold that way, and then take the type 2b string theory on X, on X times R4. So in string theory, the spacetime should be 10-dimensional. We take those 10 dimensions, so 6 of them are this Calabi-Yau threefold, 6 real dimensions. Take that cross R4, and that's supposed to be another way of producing this class S theory. And so sometimes in the mathematics of this class S theory, you see this Calabi-Yau manifold show up. And so I'm trying to say why. Okay, fine. So all fibers are singular. Now then the next thing you can do is you can smooth out the singularity. So you can move in the moduli space of this Calabi-Yau. Okay, so that's what I'm going to talk about now. But the way you initially define it is to take the singular one. And so in the sense of AN-1, so we're always doing the class S theory for, I'm describing the case of the Lie algebra AN-1. Here, actually, you could also take D or E if you take different quotients here. The first story was only for A. Okay. So, all right. So let's try to talk about Coulomb branches. Yeah. Yeah, so I think that today even exists has to be understood in the physics language, not in the mathematical language. So I don't think that there's a completely sharp definition of, as a mathematical object, what is a quantum field theory in any dimension? So particularly, what is a 6-dimensional quantum field theory? So I'll tell you sort of various mathematical things that are downstream of that. But so this is a problem which should be solved, you know. But today, I think that there's not a, I can't answer your question. So I can't tell you mathematically what it means. Physicists think they know what it means. No, because it's not a Lagrangian field theory. So very importantly, right. So the idea that a quantum field theory comes from quantizing some space of fields, that's Lagrangian field theory. So here we're saying this is a quantum field theory which does not come from quantizing a space of fields. So it has all the outputs. So the kind of outputs that it has, you know, what you expect to be able to calculate in this quantum field theory are things like correlation functions of observables. So, if I take points in 6-dimensional space, there should exist correlation functions. If I told you what are the observables, in this quantum field theory, we know some of the observables. And so you can formulate what it means to have correlation functions. You can formulate the properties that those correlation functions should have. That would be part of the data of a 6-dimensional quantum field theory, but not all of it. So those are supposed to exist. But the idea that they're constructed by path integration over a space of fields, no. Right. Yeah. Yeah. No, there's a canonical one. Yeah, I mean, okay. We could write it by equations. It's given by the equation like x to the n plus y squared plus z squared equals 0, where x, y, and z have to be understood as living in some powers of the cotangent bundle of C. So it's one canonical Calabi-Yau manifold that we're writing. Okay. Well, the other variable is the coordinate along C. Yeah. Okay. Oh, good. Mark points. Okay. Yeah. So mark points. So far, I didn't explain the role of mark points. So the role of mark points is the following. So in this field, in this 6-dimensional field theory, so there are. So in any field theory, you can have defects of various dimensions. So for example, when we compute correlation functions, there are local operators. Those are like things that you put at points of the field theory. In this theory, in addition to local operators, there are 4-dimensional defects. Labeled by the data. Again, let's just say it for G equals. Yeah. You're asking me how to get from. Yeah. So the basic statement is that it's not mirror symmetry. It's a kind of M theory string theory duality, which I think if I try to describe it now, I won't say it correctly. What's that? Chiral? Yeah, that's right. That's right. So yeah, I guess that's right that there's a T duality involved on a circle, which I think yeah. Yeah, but let me not try to say it correctly. Okay, so to answer this question about where the defects come from, so the statement is that in this 6-dimensional theory, there exist 4-dimensional defects labeled by, in this case, by Young diagrams. And more generally, you would say labeled by like nilpotent orbits of the Lie algebra. So then the idea is that when we put, so we're putting this x of g on, I said, R4 times the Riemann surface. But then inside of there, we can put the defect on R4 times a point. And so that produces for you the marked points on the Riemann surface. They come from these 4-dimensional defects that you just put on. Yeah. Good. Okay. So, okay, I guess I don't talk about Coulomb branches now. So let me instead say one other thing which we will need. So let's talk a little more about this conformal symmetry. So the one more remark. So these theories, these n equals 2 theories, the theories of class S, which we talked about so far, they're n equals 2 theories, but they have another property, which I didn't emphasize, but should have, which is that they are conformally invariant, in particular scale invariant. And so sometimes you write it like this, SCFT. So they're invariant under changes of scale. Not every theory in the world is conformally invariant. And in particular, these theories we can deform by adding some parameters. I'll call them mass parameters. So in a conformally invariant theory, all the particles are massless. Because if you have a mass, mass is kind of dual to length. So having a mass scale is like having a preferred length scale. So conformally invariant theories, everything's massless. Sometimes we want to study theories of massive, including massive particles. So we take the conformally invariant theory, we can deform it by mass parameters, and the mass parameters live in the Lie algebra of the flavor symmetry. So at each puncture, there's some parameters that we can adjust, and when you turn on those punctures, you destroy the conformal invariance, destroy the scale invariance. Okay. Then once you start doing that, then you can play various other tricks. So for example, you can do more complicated things. For example, you could send one of the masses to infinity. Okay, you can just do that. Or you can do kind of coherent things where you send one of the masses to infinity at the same time colliding mark points. And in this way, you can get some other interesting examples. So I just mentioned one of them because it's a useful example to have in your mind, which is, okay, our favorite thing, the SU2 theory with 4 flavors. So this one is conformal. All the particles are massless. Now, suppose I turn on masses, M1, M2, M3, and M4. I take all the masses to infinity, and at the same time, I collide points 1 and 2 and points 3 and 4. Then I can produce a theory with 2 punctures of kind of more complicated nature. So this was the theory with SU2, gauge group SU2, and matter C to the 16. And by sending the masses to infinity, what I'm essentially doing is getting rid of the matter. I'm taking the particles that are massive, I'm taking the particles which were massless, and I'm making them not only massive, but I'm making them infinitely massive. The more massive the thing is, the less I feel it in kind of low energy processes. And so taking the mass to infinity is like getting rid of those particles. And so what I wind up with here is, again, a theory with gauge group SU2, but now with no matter at all. So this is the simplest one. This is the one that was originally studied by Seiberg and Witten. So it'll be a useful example for us. So I just want to say that that one we can also realize in class S, but by this slightly more complicated construction. You mean what's sort of sitting at the punctures? You mean when I do it, how do I? Yeah, it's like I think it's the mass times the separation. So I hold like m times so. Yeah, I mean, in some sense, there's nothing that remains invariant. I mean, this field theory is a different field theory from this one. I'm not saying it's the same field theory. The only question is to take this limit in such a way that the theory that you get is actually an interacting theory. You don't get just a free theory. For that, what you're essentially doing is you're taking the mass to infinity And at the same time, you're taking the coupling to 0 in a kind of tricky way. In such a way that, I guess one way you could say it is the following. You know how in quantum field theory, you have a renormalization group. So you have an effective coupling at any given scale. And what we're trying to do here is we're trying to arrange that you take this limit in such a way that the effective coupling at a fixed scale remains finite. And that way you get an interacting theory here. What's that?
You have a physics conformal physics that
maybe we can discuss it afterward. I think.
We have the whole point of this.
Yeah.
We have the 4 point on the scale, and then you have the 2 point work, and then you can get some kind of shift. You have some kind of the effect relation. Sorry, CFD Western.
I mean,
that's I think that's an important that would be proper star, and then the other 3, 4, and then the star star. That's the one thing that that's why we'll call it kind of thing.
I think in the language of, if you want to say this in the language of two-dimensional conformal field theory. So indeed, okay, so this is related to something in two-dimensional conformal field theory, right? But right. But suppose for a second we talk about the dual two-dimensional conformal field theory, which lives here. But then, I mean, this corresponds to a limit where, so here I have 2 primaries. And what we're doing is we're taking their conformal dimension to infinity. So it's not just like fusion. So I mean, sometimes you would think about just doing like the operator product of these 2 things, just doing fusion. That's not what we're talking about here. We're talking about a 4-dimensional theory. That's right. Okay, sorry that I have not succeeded yet in talking about Coulomb branches. So Coulomb branch will be the first thing next time, I promise. All right, thanks.